So thanks to the organizers for this opportunity. This is my first visit to Vienna, and it was very enjoyable to have like 7 days without rain. I am in the UK, so this was perfect weather. Good. So I'm going to talk about some work with Robert and Samuel. And Robert has told you sort of all the interesting details, and I'll just fill in some of the gaps. And these are the papers are also up here. So yeah, I'll talk more about perturbations, and I'll tell you like how we kind of derive cosmological observables from an abstract matrix model using our approach. So I have the opportunity to show you some nice pictures because I don't have much opportunity to show nice pictures later on. So I'll start with here and ask this question that, we're really interested in a very early universe, and perhaps not in this crowd, but typically when I'm giving this talk to cosmologists, the standard answer is, but don't we already know that theory? That's inflation. And again, you have had a dose of why inflation is not the only theory that is consistent from Robert before lunch, but perhaps you've forgotten over lunch, so I'll refresh your memory. And of course, inflation is a beautiful theory which postulates an early phase of accelerated expansion. And not only that, it solves all the standard horizon problem, etc. But it does something more. It makes these amazing predictions for quantum vacuum fluctuations being turned into late time inhomogeneities, which we can observe as temperature and isotropies in the CMB and so on, as Robert pointed out. But of course, inflation has some shortcomings as well, like any theory, which is to say that inflation is sparsely incomplete. There's famous theorems about this. And we need to ask what came before inflation. So even if inflation is eternal to the future, it's necessarily not eternal to the past. That necessarily means how do I set initial conditions for inflation? And this is, again, just a cartoon to show that, the inflation doesn't solve the so-called singularity problem, etc. And this is long known now. And space-time can be completely different, like fluctuating objects, not smooth manifolds that we're used to in classical space-time. So what are the initial conditions for inflation to begin? And this is a very well-known, very well-studied problem over the years. And one perspective on it, just to give you, like, again, a very simple perspective on it, is to say that, the standard cartoon for inflation is that we have some inflaton field which is rolling on some almost flat potential, and then we have reheating, etc. But that requires that there is a minima for this field. So one question to ask is, why was this field displaced from its minima at all to begin with? So why did the field start out at some region where it can have this slow roll part and displaced from this minimum? I'm not saying that there are not any answers to these questions, but these are not resolved. And what's more important, I think this is kind of agreed upon, that inflation by itself as an effective field theory cannot answer these questions. You have to embed it in something else. So that's one way to think about it, that can we embed inflation in string theory? But if we want to do that, why restrict ourselves to inflation? Can we embed an early universe cosmology in string theory? So that's kind of the broad thing that I want to talk about. And just at the very beginning, I want to make this distinction between what goes under the names of, like, loop quantum cosmology and so on, which are essentially just toy models, which are, let's say, inspired by quantum gravity. So they just borrow some quantization techniques from some quantum approach and apply them to simple toy models to see how the early universe should have begun. And that's not the path that we want to take, because what this kind of an approach lacks is stringent consistency checks. So it's difficult to know. I mean, if you just start with FRW cosmology in this mini superspace approximation, you can do a lot. You can quantize it in whatever way you want. And it's not clear that all of those quantization procedures are consistent with respect to symmetries of the universe and so on. What we want to do is the opposite. We want to coarse-grain some large-scale cosmology starting from some very fundamental UV degrees of freedom, which can be abstract degrees of freedom. In this particular example, of course, I will talk about matrix degrees of freedom. That makes it a little bit hard, of course, because this top-down derivation is always difficult. We don't know how to coarse-grain this. We don't know how to extract some information about large-scale structure from some very abstract mathematical models. Of course, we have to still solve the standard cosmological puzzles and, hopefully do something more, give some falsifiable predictions. And Robert has kind of told you our approach or our ideas about how we can coarse-grain matrix models to get a cosmology out of it. The work is nowhere near complete, but the idea is that it's possible to do that. This is an ambitious thing to do, but there's a very high reward. The high reward is that we're not doing some toy model approach. We're not starting by saying, okay, this is just some FRW. I'm going to take the symmetric part of GR, some symmetric solution of GR, and quantize it in some way. That's not what we want to do. So if we are successful, this would be some sort of new model of cosmology. And if we end up not getting inflation in the early universe, that's okay. All we need to do is solve this kind of standard puzzles, like the flatness and horizon problems, as Robert was mentioning, and give out our predictions. And then we can go back and check whether those, when we confront our predictions with observed data, whether this model is a good one or not. And as I will show you in this particular approach that we will follow, there are not like this whole field of arbitrary tunable parameters or something like this, because this is not an EFT. We can't just add extra terms in the potential, for instance, to tune to what we observe in the sky in case our model falls short. So if it is ruled out, it's kind of ruled out. We don't have so much to play with. All right, so that's kind of the takeaway message, that we are trying to build an alternative description of the early universe from the BFSS matrix model. But I'm just going to restrict myself to the BFSS for today, just for constraints of time, and this is what we did first. But we have started to do this also from the IKKT model, and a similar approach can be applied to that. And we get results which are consistent under duality chains that we know relate BFSS and IKKT. All right, so Robert already told you about all of this stuff, that this standard Big Bang cosmology does a lot of things successfully for us, like existence of CMB and so on, but it also has a lot of shortcomings. These are things which you already know, this horizon problem and so on. So this is like, again, just a standard picture for the horizon problem. Why are things so homogeneous on large scales? So as Robert had a wish list, but I think that one has been erased, so I decided to write this down again. So we want to solve these problems, and the one that I am going to focus on for my talk is this origin of structure, that we want to derive from our model a scale-invariant power spectrum of adiabatic perturbations for both scalar and for density perturbations and tensor modes. That's the part that I'm going to fill in the gap of what Robert said. All right, this you have seen, and Robert mentioned string gas cosmology and bouncing models, and this is just, again, a list of models which kind of does this. So this is just to show you that there are examples. I mean, I keep saying that there are alternatives to inflation, and I mean, that's not to say that all of these don't have their own shortcomings. That's true, of course. All models have their own shortcomings, but it's possible to get a scale-invariant spectrum in particular, because that's the thing that I'm going to focus about, from other kind of geometries, which don't have to be almost de Sitter, because that's not the only way to get scale-invariant spectrum. I mean, for instance, for bouncing models, there's a perfect duality between a contracting phase and this accelerated expansion. Okay, so you've seen this many, many times now. This is the BFSS Lagrangian BFSS action, and then there's obviously also the IKKT action. And we know there's this 9 bosonic matrices and their superpartners, etc. So this stuff you all know, so I'm going to go quickly on this. And as has been described throughout this workshop, the beautiful aspect of these models is that space-time somehow emerges from this eigenvalue distribution of these bosonic matrices. And we don't understand everything about it. We don't understand how we get a 3+1 large universe from this, etc. But work is very much under progress, and there's a lot of advancement has been made. But this, I think, more or less, all of us, at least in the room, agree about that there is a emergent description space-time, even if it is not exactly what we observe. We haven't been able to do that much, but there's an emergent description space-time from these matrix models. And what, again, I will show you in a couple of slides, that, as I said, like, if you start with this kind of a Lagrangian, I mean, when I give this talk to cosmologists, the first question is, where is the scale factor? Where is the metric that we are familiar with? How do you get those things out of this? And those are not easy things to do, as we all know. And there are different prescriptions for doing that, as we also have seen. But the important thing is that the price that you pay for this, you get rewarded later on. as I will show you again in a couple of slides, by not having this abundance of free parameters. So this is a Lagrangian. I just can't keep adding terms to this willy-nilly, because that will completely destroy the relationship matrix models have with string theory, for instance. So if we have to add some term to it, like a mass term, etc., there has to be a very good justification for it, and then we have to take some limit in which that goes away. So we can't just keep on adding. I mean, for instance, if I start with this model, I have a prescription of deriving cosmology for it, and I derive some power spectrum that is not scale invariant, that is a very large red tilt or something. Well, that rules out my prescription, essentially. That just says that, no, you cannot coarse grain in this way. I can't go back and add another term and try to fix that. That's the main message. This is the same thing. So this is a consistent, this is a principled approach, and there's a lot of promise of rich phenomenology. I just mentioned this point because that's the only thing that I'm going to focus upon today. Robert already told you this is not an EFT description in the sense of quantizing Fock modes. So there's not the usual cosmological constant problem in these models. And because this is like a model that comes from string theory, so there's like we expect that there will be no singularities in this problem in this approach. Okay. So now for a little bit more details, if you have gotten the big picture by now. So I consider this thermal state in the BFSS, and as Robert was mentioning, so I take this high temperature limit. So why is it? Why should I do this? Well, in this particular case, of course, I want to compactify this on this Euclidean thermal circle, and I want to study perturbations. I want to study thermal fluctuations. That's my main reasoning to do this. So why am I in the high temperature limit? So one very simple reason or very operational reason is because I want to be in the perturbative limit so that I can use standard perturbation theory to do my computations. That's one reason. And of course, in the early universe, we do expect like a high temperature thermal state in any case. If I do that, then I can rewrite this BFSS action in this form. I'm just not writing down all the terms because there's a lot more terms here, of course. And I've obviously expanded all of these fields in this Matsubara frequencies, etc. So what we can recover from this once I expand this and plug it back into the action is like the bosonic IKKT term plus some kinetic term and interaction terms. Again, I'm just writing this down because the other terms just make things look very ugly. So this is well known. So I just want to give a disclaimer at this point, partially because of the discussion we had after Robert's talk, is that I'm just starting with the BFSS because that's what we started with. We wanted a starting point, and that's what we did in our first paper. But what we have shown subsequently is that we could have just as well started with the IKKT model and had done the same thing. So of course, in the BFSS, there's an intrinsic time parameter, and so it's somewhat easy to Euclideanize it and compute the thermal partition function. But in the IKKT model, you can do the same thing, compactify the A0 matrix a la Washington-Taylor, this method of images. And what you would find in that case, which is detailed in this paper with Samuel, is that you derive a very similar partition function. The only difference is when you actually compute observables, you would find, like we do in the BFSS model, you get a scale-invariant spectrum, but the amplitude of the spectrum is slightly different. It's some order 1 number difference there. So maybe some factors of 10 or factors of 13 over 7 or something like this, which is different. So that's just a difference in the prediction for cosmology. But there's a well-known way to, I mean, of course, we have to like do this temperature goes to 1 over temperature kind of rescaling, but then these two models are completely equivalent in that sense. So I could have just started from the IKKT if I wanted. At that time, we started with BFSS. That's a disclaimer. I won't go into the IKKT because I wouldn't have that much time. So now, yes. Yes. Just some order 1 numerical factor, like some 13 over 7 or something. This is just for the observables that we would compute. And I will show you what we get for BFSS, and then you will get a better idea. No, that's exact. So that's exact. But even when you write down the partition function, there's like a particular thing that you extract from it to get your cosmological observables. And the way you extract it, that involves different derivatives of different terms in the partition function. So that gives you this order 1 change difference. And we can discuss this once I show you how we do this. Okay, so what is important in the BFSS is if we really stick to the BFSS, and that's what I'm going to do, we can't just look at the the leading order term. You have to include this 1 over t corrections. I mean, that's just necessary for cosmological perturbations. And just as in the string gas cosmology, what we are interested in is to compute the infrared, the spectrum for infrared modes, for infrared perturbations. And so it can have something very different in the UV, but what does it do for the infrared? That's what I want to compute in this case. So there's a lot of, again, this is for mostly for when I talk about this to cosmologists, I tell them that, you know, there's a lot of exotic things that I'm telling you. I'm starting in matrices and I'm deriving cosmology from it. But this is not the exotic part of it. And this is also somewhat less familiar because people are very much, you know, they grow up with inflation. So they imagine that vacuum fluctuations are the only way to account for late time inhomogeneities. That's just not true. A thermal state has been used also, I mean, of course, in string gas, but in other approaches, like for instance, for warm inflation. So in variations of inflation, warm inflation, which was discovered by my colleague at Edinburgh, Arjun Barrera, they do consider thermal fluctuations. So again, vacuum fluctuations are also not just particular to inflation. In ekpyrosis, people use vacuum fluctuations. So thermal fluctuations is not something that is exotic to matrix models or string theory. This is just, there are two distinguished states for the early universe. It can be the vacuum state or the thermal state. And it makes perfect sense to choose either. If you choose the thermal state for standard inflation, then you just not get a scale-invariant spectrum. So you have to modify that, and that's the warm inflation picture. And similarly, in this case, we're choosing a thermal state because that makes more sense. Not the vacuum state doesn't make that much sense to us, at least in our approach. This is well known. If I have a thermal state, how do I compute the spectrum of density perturbations and tensor modes? This is well known, and they all come from some fluctuations of the stress energy tensor, which can be computed from the thermal partition function. These are the things so these are all these sources that I've written on the right-hand side, and these are the things I need to compute. For instance, for the density perturbations, for the spectrum of that, I need the specific heat capacity. And again, this is true irrespective of this model. This is a general formulation that you can find in this nice review. And this is going to be true how I use a thermal state to compute cosmological perturbations. That's what this is telling us. Good. So now that I know what I need to compute, I can just go ahead and compute it. I'm doing, like, as I mentioned already, like this expansion in some small parameter and doing a perturbative one. So again, this is just to rewrite that equation. So I can compute the free energy up to next to leading order as I promised. And this is what it looks like. It depends on two parameters, the temperature and this radius. This R is related to this extent of space parameter that Nishimura showed yesterday and others have as well. So this is like computing the free energy in a box of radius R at some temperature T. And that we can compute using already what was known for the BFSS model. And what is, okay. So how do we do this? This is a, I think, quite well-known calculation, again, by Jun and collaborators from 2007, that you just integrate over the non-zero modes, and you arrive, like, you know, because we want to expand around the IKKT background, that was the original story that we are doing here. So you use this kind of a formulation, and you can compute this. I don't want to go into details. I have around 10 minutes, right? Okay. Okay, perfect. Of course, we need to do a lot of approximations to do this. You need to do approximations to involve higher moments of this, I mean, higher correlation functions and etc. of the zero modes. And what turns out is that this has a well-defined thermodynamics for d equals 3. So again, this is an input in here. I'm assuming from numerical simulations that, you know, in the end, I will have in the early universe phase, after the spontaneous symmetry breaking, I'll have 3 large dimensions. This is not something that I'm deriving in here. So this I'm plugging it in here, that I have 3 large dimensions. Yes.
I'll ask a question. Did this formula from put in some kind of
It's just d-dimensional. I mean, not even 9+1. Like the d and the p is just arbitrary there. I mean, it doesn't have to be 9+1 is what I'm saying. So this d is is whatever is the number of bosonic.
My basic question is how you relate this in whatever.
Oh, no, I'm assuming that this, I'm saying that this is the free energy that I'm going to use is the 3 plus 1 dimensional one. I'm just assuming that this is the d is equal to 3 and the corresponding. Yeah, so there are 3 large matrices. That's these. Yes. Oh, this is right. So this is just for some general d, some general bosonic matrix, d number of bosonic matrices, and it's fermionic superpartner speed. Yeah. So just think that this is I can write comma d if you want. I mean, I'm going to apply this only for d equals to 3. So so in the dimension that where they exist, this is the dimension. The number of bosonic matrices. This is the BFS model, but you can have like little BFSs and so on. You can have toy models of BFSs. So I'm going to assume that this is not. Yeah, that's what I mean. Yes. Okay. Yeah, so that's this. I mean, the supersymmetry is anyway broken because I'm putting anti-periodic boundary conditions of the fermions, and this is thermal. Sorry? So the supersymmetry is broken anyway, that's what I'm saying. Because it's I'm taking anti-periodic boundary conditions for the fermions. Yeah, but I'm only computing this in a particular thermal state, and that is breaking supersymmetry. So that's a BFSS Hamiltonian, yes. Oh, that's right. So the BFSS model, if I do not impose this thermal state in this particular number of d and p, that will be supersymmetric. But anyway, I don't care because I'm going to break it anyway. In p equals 4, I don't know off the top of my head. Yeah, probably, but I don't remember like the details of that. I mean, it's not. It's That's right. So this is that's what I'm saying. So for d equals 3, p has to be 4. So it's tailored such that this is still supersymmetric before I impose a thermal state. Supersymmetric. Because the d equals 3, p equals 4. Yeah, so the d equals to 3, p equals to 4 is a supersymmetric Hamiltonian, but then I'm imposing this thermal state, which breaks supersymmetry anyway. So this is, yeah, the p. So to answer, like I think what Gautam said is like the best way to say this. Like the p is fixed to be 4 for d equals 3 to preserve supersymmetry. Okay, maybe I can just go on and we can come back to this because I want to show you the main result, which is, okay, now because you have this free energy, you can compute all the quantities that I mentioned on the previous slide. And once you compute them, you can just plug it into this formula also that I showed you in the previous slide to compute the spectrum of density perturbations and the tensor modes. Let's use that. And this is kind of the main result. So again, I'm glad I reached this slide to say that there are some order 1 numbers here, which I haven't written down because those are boring. And you find that this is a scale-invariant spectrum for both zeta and h. So of course, we don't understand why this is exactly scale-invariant, except for what Robert said, that, okay, you expect this to have this holographic scaling, because that's what they found also for string gas. But this is an intuition, and you find that it is the case. So this is again related to the fact that this is related to r squared appearing over here, which is chi1. And if you had some other dependence, then this wouldn't have been scale invariant. That's to say this is not automatic. If the free energy was evaluated and it was something else, then it wouldn't be the case that this would be scale invariant. The UV modes for the density spectrum, there's a UV part of the spectrum that is not scale invariant, that has a Poisson spectrum that goes as k squared. But for the tensor modes, it only has a scale invariant term. But of course, this UV part doesn't have any direct observational consequence. So it doesn't, I mean, it is a distinction from standard inflation models. But I mean, a lot of inflation models put a bump in the UV part, et cetera, to create primordial black holes and so on. No, they don't. No, because this just depends on the R squared that appears here. Yeah. I mean, the D and P just essentially fix some disorder 1 numbers out here. So the other thing is that, okay, but this is not exactly scale invariant because we will get like a small spectral tilt from next, so I went to next to leading order, so next to leading order, and also maybe the details of the symmetry breaking phase, that those things will give me some spectral tilt. There is the point, this slightly subtle point about the tensor to scalar ratio, which depends on this small number alpha. Because I have less than 5 minutes, I won't go into it. If someone has a question, I can come back to it. So maybe, so my only this bullet point, the only main message is that, this direct observations, like for the power spectrum, there's no difference, of course, and it matches what we expect. But there can be differences from standard inflationary models when we compute like the tilt and so on. And this is very much work under progress. That's what string gas did. They predicted a blue tilt. Maybe we'll do the same thing. What is also important is that we have to assume that there are 3 large dimensions, but we didn't have to assume anything for the exact expansion rate of this chi1. And this is related to the fact that this is dependent on how does the extent of space parameter expand. That we did not have to plug in anything about that. It's just R squared is sufficient to show the scale invariance of this result. So somehow this is reminiscent of inflation in the sense that many details of reheating we don't understand, and yet inflation can unambiguously predict things like a scale invariant spectrum. Similarly, many details of this symmetry breaking, of course, I don't know, but still there is this nice feature because of the way that this free energy shows up that you get a scale invariant spectrum. And again, I don't understand exactly why it happens, except for this heuristic intuition that is matching with string gas, and there's this holographic scaling. Again, as I promised, if you look at the final results, there's not much to play with. As I said, these order 1 numbers are really numbers. There's some numerical factors. And I can't go back, even to leading order, to next to leading order that I calculate, the temperature falls out of the calculation for the spectrum. So even it doesn't depend on T. So next to leading order, the T will come in probably, but there's not, in any case, a landscape of tunable parameters here. I can't play with a lot to make this go right. All right, so let me conclude. This is some work that I just want to advertise on the very last slide that, it has been notoriously difficult to find de Sitter. I mean, depending on which side of the debate you're on. But we have been able to have one approach to that using coherent states. But the main talk that I wanted to convince you about is that there's a new way towards a UV complete paradigm for the early universe. The nice thing is there's a whole lot of numerical evidence, thanks to many people here actually, which supports this emergence of 3 large spatial dimensions. Hopefully we'll be able to concretize this. As Robert showed you, there's a coarse graining that we adopt for time and space and the metric. The thermal fluctuations are what source the cosmological perturbations, and that gives us a scale invariant spectrum. Again, Robert showed you how the horizon and flatness problems are solved. And there's a chance that we don't have this usual vacuum energy problem, at least. I mentioned this already. There's perfectly possible to work with the IKKT model instead of BFSS and do similar calculations. Just so happened that we started with BFSS, and that's what I presented today. I believe this is very promising, but there's obviously loads of things to be done. For instance, Robert mentioned this important thing that how do we connect this to string gas? So there's some, again, heuristic connections that string gas in this emergent phase, or this non-geometric phase, was modeled by a p equal to 0 phase, where the scale factor does nothing. If we compute the background energy density for this model in that emergent phase, you find, again, this p is equal to 0, actually, the pressure. But I mean, that's just a heuristic connection. We need to make this more concrete using these solitonic states that Robert mentioned. Of course, there's lots to be done in terms of observations as well. We can go and compute the bispectrum, etc. We have to still understand how what this UV part of the spectrum can do for us. Maybe there's some indirect signatures it can give us. and so on. Okay, I'll stop here.